Hello everyone, this is Professor Keen. This is a continuation of my previous lecture on Chapter 17 of A Student's Guide to the Great Physics texts. I'm talking about Pascal's description of life under a sea of air. The idea is that our entire atmosphere weighs down on us, and that explains a lot of the kind of things that had previously been attributed to the horror of a vacuum. And so the question we left off with last time, so let me just put a title on this, Life Under a Sea of Air. Oops. Life Under a Sea of Air. And the question that we left off with last time was how much does our entire trouble here. How much does our entire atmosphere weigh? This might sound like a very difficult question to answer, but Pascal has a very interesting strategy here. So let me explain his strategy. What he says, I'll draw a picture first and then write the answer, and then I'll show how he does the calculation. So the idea is that here is, actually let me use a different color. So here's the Earth. Okay, there's the Earth. And the Earth is surrounded by, and this isn't to scale of course, but an entire ocean of air. So this is air right here. And he mentions that, we can figure out, we know how big the Earth is. And we can try to figure out how much this entire atmosphere weighs. How do we do this? Well, he says, we don't really know how tall the air is. We would kind of need to know how much air there is. But we do know how big of a column of water is supported by our air. And we know that the air can support a column of water that is 32 feet deep. So, in other words, our entire atmosphere weighs the exact same amount as if the entire Earth was covered with an ocean that was 32 feet deep. Because after all, when we have air, it can support a 31 or 32 foot tall column of water. So the weight of all this air is the same as the weight of a 31 foot deep ocean of water that is covering the whole Earth. So his answer is the same as an ocean of water that is 31 feet deep, covering the Earth. Incidentally, it would also weigh the same as a 760 millimeter or 76 centimeter deep pool of mercury covering the entire Earth. So the pressure that we here on Earth feel, here's us standing here on Earth, is the same pressure as if we're at the bottom of a 32 feet deep pool of water, or if we're at the bottom, if we're laying down at the bottom of a 76 centimeter deep lake of liquid mercury. So this is going to give us a strategy for calculating. So how do we calculate the weight of all this air? Well, it's going to be the same as the weight of all this water. So the first thing we do is we find out or look up, find the surface area. This is the strategy that Pascal pursues. find the surface area of the Earth. There are several ways to do this, by the way. This is the way he does it. And we're going to do this in square feet. This was known at the time. Number two, we multiply this surface area by 31 feet to find the volume of the ocean. Of water. Okay, so that'll tell us the volume of all this water. So it's basically the surface area of the Earth times 31 feet deep. And then step 3, I'll get rid of these. Step 3 is then multiply the volume by 72, because each cubic foot of water weighs 72 pounds. So 72 pounds per cubic foot. And that is going to allow us to calculate the weight of that ocean of water, and hence the weight of the ocean of air under which we live. So first, let's find the surface area. Well, the surface area is equal to, the surface area of a sphere is equal to the diameter of the sphere times the circumference of the sphere. I don't know if you think about this way, but if you do this, you end up getting 4 pi r squared, by the way. And so we know that, I'm going to approximate this. So we know the diameter of the Earth is about 8,000 miles. And you multiply the diameter, 8,000 miles, by the circumference of the Earth, which is about 25,000 miles. Okay, of course, the circumference is a little bit wider at the equator than measured in other locations, but we're going to use the circumference at the equator. And so when you do this, you get about 200 million square miles. Okay, or we could convert this to square feet by multiplying by 5,280 squared, and we end up getting, I'll use scientific notation, about 5.6, I'm not doing this in my head, I did these calculations before, 5.6 times 10 to the 15th square feet. So that is the surface area of the Earth. And then step 2, we'll calculate the volume of this ocean. And we just multiply that by 31 feet deep. And so we get 1.7 times 10 to the 17th cubic feet. That's the volume of an ocean that's 31 feet deep, covering the whole Earth. And then finally, we can multiply that by 72 pounds per cubic feet to get the weight of the ocean of water. So the ocean of water, or alternatively the ocean of air, that's as deep as our entire atmosphere. And when you do this, you get 1.2 times 10 to the 19 pounds. By the way, Pascal's answer, he did it with fathoms and leagues and things like that, but he got 8 times 10 to the 18th pounds. So, about maybe 20 or 30% different than what we got. So this is almost 1 times 10 to the 19th pounds. So that is a strategy that Pascal used to figure out the weight of the entire atmosphere of air. This is really fascinating that he was able to, by simply measuring the height that water could be pumped up in a tube, or the height of mercury that can be drawn up into a tube, he's able to find the weight of the entire atmosphere of air.